All right, so it might seem kind of weird here, but we're going to go to section 8.7. We've been talking about in chapter 9, looking at solutions to quadratic equations. So now we need to deal with what happens if we have negative values. So meaning we don't have real solutions. So negative values like under the square root, so like the discriminant. So we're going to talk about what do those kind of parabola or quadratic graphs do? How do they behave? How do we work with those numbers? So these would be like the parabolas that don't cross the x-axis would have solutions that are complex or imaginary. So we want to be able to deal with those as well. So we're going to do a little bit, a couple parts here of just talking about imaginary and complex numbers, and then we're going to come back to solving quadratics and see how that fits into the bigger picture here. So complex numbers are things that have real parts and imaginary parts, and the imaginary unit that we're going to be using is this letter I, so I for imaginary. So complex numbers are made up of both the real and imaginary parts. So we're going to talk about what that all entails. So imaginary units, again, or we use this little cursive I, is defined to be the square root of -1. So when you hear someone saying I or talking about I, that's what that means. That means I squared would be -1, because you remember when you multiply a radical times itself, you always get the expression underneath. So these are kind of our two basic definitions that we're going to be dealing with. So that imaginary I is squared -1, I squared then would be -1. We can take any radical then and break it apart using that product property and think of every single negative radical as the square root of -1 then times the square root of whatever the number is. So think of just b as any number. When I multiply those together, I get back to that original expression. But what's nice about doing this is we separate out then this imaginary unit, this imaginary part, and we can call that I then times the square root of b, and we can do what we normally would with that radical. So a big part of today is going to be dealing with simplifying and breaking things down that are imaginary underneath, so we can deal with the number part and be able to solve. So we're going to spend quite a bit of time today on that, and then we'll work into operations and things as well. All right, so let's talk about the complex number system then, what this all means. So when we say complex, if you think about the word complex, that means usually means to people that things are kind of complicated, right? There's a lot to it, and that's very true with complex numbers. It's anything of the form a plus bi. A plus bi meaning we have a real part and an imaginary part, that imaginary unit, the I. So we have both a and b, these coefficients are real numbers, so when we look at those. So basically complex numbers break down into two different groups. You either have real numbers or you have non-real numbers. So non-real, so real or not real, right? And so when we talk about not real, that's what we're talking about, like imaginary solutions. So that's where that word comes from. When you think about imaginary, that usually means the opposite of real, right? So when we think about that, that's kind of where that term comes from. I always thought that was kind of funny, but you either have real or not real. So a real or imaginary solutions. If it's imaginary, that means you have something that has that unit I in there. So the a plus bi kind of situation, but the b can't be equal to 0 ever, because then it wouldn't be imaginary anymore. So you could have things like, 3 plus 6i, that would be an example of an imaginary number, or just the imaginary part, 4i would be fine. The a could be 0. Or you can have these square roots of negative numbers, right? That's going to have an imaginary unit. So that's really where we're going to be focusing our attention right now, is on this non-real category. But we know everything about real numbers. We've talked about these before, where you can have either rational or irrational. So ir meaning not, right? So rational or not rational. We made this little chart before. If it's rational, those are things like that don't stop or don't repeat. So like square root of 11, pi, things like that. Rational numbers, that's a ratio of integers. Remember, that comes from the word ratio. So a ratio of integers. So things that do stop or repeat. So when we deal with the real number system, I think we're a little bit more confident there. So rational can either be nice integer values. So like 3, -5, those are all like integer values, or they could be non-integers, so they could be just ratios things. So you can either have an integer or not an integer. So things like 2/3, it's still rational. 7, -7/2, still rational. It's just not an integer value. So we know kind of how to deal with the real number system. I guess what we're going to focus on is the not real or imaginary parts today. But we're going to be dealing with all these different types of number systems when we solve quadratics. All right, so let's talk about how we simplify things that are negative values underneath or imaginary. So think about what this first one means, and I'm going to go ahead and see if I can move that over here. So we can just focus our attention on this first one. If I asked you to do this before, you'd be like, nope, sorry, you can't do that, right? Because the square root of negative 25, think about what square root means. What number times itself gives you a negative 25? Well, there's nothing that times by itself to give you a negative 25, because the only way you can get a negative sign is if your signs are opposite, right? That's the only way you can multiply to get a sign that's negative. So that doesn't work when you're multiplying something times itself. So this is impossible, oopsies, in the real number system. So there's only going to be one possibility, and that's if it's imaginary. So I need to think about what that imaginary unit means. So we're going to use our product property for radicals. And every time I start with a negative, I'm going to write it as a product of -1 times the number. So this is just kind of our process that we're going to deal with to get that imaginary unit out, so we can deal with the regular real part of the number. So I'm writing it as a product. That's that product property we did lots of times before. If you have a product under a radical, it's equal to the square root of the first times the square root of the second, right? We can break it down. So why did I do that? Well, the square root of -1, that's I, right? So I can simplify that and write that as an imaginary part, and then I can deal with this other part and do what I know I can do. Square root of 25 is 5. Now, instead of writing I times 5, which would be super, I think, awkward for people to say, we will probably write that coefficient part first. So 5i. So I can actually simplify this, and it's going to be an imaginary unit. So when we think about what's happening, we take that negative out of there. Let's talk about the next one. So this brings up another issue that we've dealt with quite a bit. When people see that negative on the outside, kind of causes a little bit of kind of angst, I guess, but it just means your sign of your answer is going to be opposite whatever it would have been. That's totally fine. So this is completely okay. What's not going to give us a real number is what's going on the inside. That negative, that's the same issue we had with the last one. There's no number times itself that gives you a negative answer. So we're going to get that negative out. So here's how we're going to deal with this. So we have our negative from this minus out front, and we're going to think of -81 as -1 times 81, which I think everyone would agree is equivalent to -81. But why did we do that? Because then we can simplify this product. Square root of -1 is I, and then square root of 81 is 9. I can do those two parts separately. It's taking out that imaginary unit. Now, again, I would probably never write the 9 behind the I. I think it's a little bit easier to say -9i. And again, the reason this was negative was because of that minus sign up front. So we're always going to be separating out that imaginary part. All right, let's do some more so we can practice kind of doing operations with I. So just like in the last situation, see how I have both of these as negative radicals. The very first thing you're going to do for each one of these is write it as a product. I'm going to take out that -1 for each of those products. Any negative root that you have, always take out that -1 times the number. It just makes it easier to deal with our imaginary pieces. So -1 times 6 and -1 times 5. Now do whatever you can. So square root of -1 is I. So I have I times the square root of 6. And I have another one. So another I times the square root of 5. Now, when we multiply, remember, we can multiply things in whatever order we want. So I'm just going to do a little rearranging here. We have I times square root of 6 times square root of 5. Now, some people might never show this green step that I just did, but I wanted to do this to illustrate a point of what you can do in your head. We're going to multiply together the things that we can. So I times I is I to the second. Square root of 6 times square root of 5, neither one of those are perfect squares. So all I can do really is just multiply them together. That would be square root of 30. And then I'm going to take a look and see if I can do anything with either of these. I squared, let's go back to our definition here. I squared is the same as -1. It's a square root of -1 times the square root of -1, which is -1. So I can actually do something with that. That's going to be -1. Square root of 30, kind of stuck. 30 isn't a perfect square, right? There are no perfect squares that divide in there evenly. If you have your perfect squares sheet that we have from beginning of chapter 8, this would be a really great time to kind of have that sheet out so you can double check. But your perfect square is 4, 9, 16, 25. None of those divide in there evenly. That's as far as I can really go. So this would be equal to -1 times the square root of 30. So you don't need to write the 1 out front if you don't want to. It might be a little bit easier way to simplify and talk about that. All right, let's take a look. Oh, I think I skipped a couple, didn't I? I didn't even see them. Sorry about that. I didn't scroll down on the last screen. These are going to seem a lot easier then to do that. So let's go back and do letter C and letter D. Sorry about that. We can go back and grab those. That leads us into what we were just talking about. So for this first one, letter C, again, I'm going to think of it as -1 times a +7. Always get that negative out first. Get that imaginary unit out. So square root of -1 is I. This brings up a very important point. Square root of 7 is not a perfect square, so kind of like what we were talking about in the one I jumped ahead on. So I can't really do anything with that. No perfect squares divided in there evenly. So this is really simplified. That's as far as I can go. Now I know with the whole number ones, I said I'd probably put the I behind. I would be really cautious of doing this because for some people it's like, oh, is the I under the radical? Is it not? That's a little bit harder to read. So if it's a radical, I usually put the I out front. So I know that's a little bit different, but just to be super cautious, it's really easy for people to read it when it's just a whole number like -9, but with a radical, a little trickier sometimes. All right, let's talk about -44. Is it a perfect square? Nope. But I can still do the negative times the 44, always my first step. Break out that imaginary unit. So I'm going to have an I out front. Square root of -1 is I. Now 44, let's see if we can simplify that. So if you have your perfect square sheet handy, we have that list. Perfect squares, do any of those divide into 44 evenly? Well, 4 sure does. So 4 times 11 gives us a 44. So we're going to break it down into the biggest perfect square times what's left over, the same as what we were doing in the beginning of chapter 8 here. It's the same concept as what we were doing before. We just got that imaginary unit out of there. So square root of 4 is 2. So 2 times the square root of 11, and then we have that times I. This is all a product multiplied together. Now, for sorting and organizing to write my final answer, I usually put whole numbers first, then the imaginary unit, and then the radical. Again, for that same reason as the last one, sometimes the I gets lost in the shuffle underneath that radical, so we want to be careful with that. So this is what we're going to be doing to simplify, right? This is how we want to be able to talk about these values. All right, back to the other slide. Sorry about that. Kind of missed those two on the bottom. I didn't scroll down. Couldn't see them underneath there. All right, so letter B, very similar to letter A. I want you to go ahead and pause the video on this one. I want to see if you can write out what we did on letter A. Get those imaginary units out of there. What would you write -8 square root as? And what would you write -6 square root as? And see if we come up with the same thing. So go ahead and pause the video, give it a whirl. All right, so square root of -8 would be square root of -1 times square root of 8. And square root of -6 would be square root of -1 times the square root of 6. So we're starting with that same idea. Get those imaginary units out. So anytime you see a square root of -1, that's an I. So I times the square root of 8. And then square root of -1 is another I times the square root of 6. And just like the last one, I'm going to do some sorting and organizing now. So what could I put together? An I times an I. And again, some people would never write this step, but this is just what I would be thinking in my head. The I's I can multiply together, and then the square root of 8 and the square root of 6 I can multiply together. So I times I to the second. Square root of 8 times the square root of 6 would be the square root of 6 times 8 is 48. All right, now from here, it's kind of like what we were saying before. Let's see what we can simplify. So I'm going to see if I can do anything with this. I squared is equal to -1. So that's okay. And then 48, that's not a perfect square, but I'm going to see if there's anything I can do to break that down. Are there any perfect squares that divide into 48? Well, 4 sure does. 4 times 12. 9 doesn't. How about 16? 16 would be the biggest number that can divide in there. So when I take a look at my biggest perfect square, I always want to take out the largest one. So I'm going to take out that square root of 16 times square root of 3. Oops, that's a 1, sorry. Trying to read my own writing here. So -1, and then square root of 16 times square root of 3, breaking down that 48. So square root of 16 is 4. So we have 1 times 4, -1, I should say, and then times the square root of 3. So I'm thinking about everything that I can possibly do. I multiply those together. So -4 root 3 then would be my final solution. I've simplified it as far as I can go. If you didn't take the biggest value out, you would end up having to keep simplifying. So it's always looking for that biggest perfect square. All right, so let's try this next one. So a little bit different than the last couple, where one of them is a negative under the radical, but the other is just a positive. So we only need to worry about the ones that are negative underneath to take that -1 out. So when I rewrite this one, I'm going to deal with that -1 times the square root of 5, but that square root of 7 is just fine. It's a positive value, so I'm not going to worry about that. And then deal with anything that we can. So square root of -1, that's I, and then I have my square root of 5 and my square root of 7. Now for this one, I don't have any I's to put together. It's just I, so I'm going to have I in my answer. Oops, let's change colors here. But then I can do this multiplication. So square root of 5 times square root of 7, that's the square root of 35. Now we're going to treat that the same as we would any other radical. Are there any perfect squares that divide into 35 evenly? If you check your list, 4, 9, 16, none of those divide in there evenly. You can't simplify that. There's nothing I can do with that either. So that's all we can do. So sometimes there's just not a lot that we can do to simplify things. It just depends on what the expressions are that we're dealing with. So for that one, there's really not anything else that we can do for that situation. So we don't have anything else to deal with there. All right, let's see if we can jump into some division. So let's take a look and talk about some dividing. So we've been trying to deal with multiplication there. Let's deal with division. It's the same philosophy. We want to get those negatives out right away. So we have our -1 times the square root of 80, and then we have our -1 times the square root of 5. So we always want to deal with those, get those negatives out right away. So then we have I times the square root of 80 over I times the square root of 5. Now, when you get to here, think about anything. If you didn't even know what I meant, when you're looking at a fraction like this, we can always divide out common factors. There's a factor of I in the top and the bottom. That's going to divide to be equal to 1. Then all we have left is dealing with the square root of 80 over the square root of 5. Now, when we're dealing with fractions and radicals, remember, there's always two ways to deal with it. You can take the square root separately, like we're doing right now. And that's great if they're perfect squares, but neither 80 or 5 are perfect squares. That's kind of tough to deal with. So you can also think of it as dividing first and then take the square root. So my guess is always try to look at it both ways and see what's easier. 80 and 5 aren't perfect squares, so doing them separately didn't really help. But what's 80 divided by 5? Can you think about that for a sec? Divide that on your calculator. That's 16, isn't it? So actually, it's easier to divide first and then take the square root and get our final answer. So square root of 16 is 4. So it's a little bit faster. So remember, when you're dealing with division, we can look at it both ways. Either take the square root separately or divide first and then take the square root. So we're always going to look for the easiest route to take. But remember, we always have to get those negatives out first. That's the very first thing that we have to deal with. So always be thinking about that. So let's try it on that next one here. So what's the difference? Can you tell, looking visually from letter A to letter B? In letter A, both of them were negative. In letter B, only the top one is. So when I'm thinking about taking out that -1, I only have to do it in the numerator. The denominator is just fine. It's a positive value. So when I simplify this then, I only have one square root of -1 to deal with, and that's that I in the numerator. All right. Now, from here, I'm going to look to see what I can reduce. In that letter A, I could divide the i's out. And this one, I cannot. I'm going to have I as part of my answer. There's absolutely nothing to do about it because there's nothing to simplify with it. There's going to be an I. It's an imaginary solution. Let's talk about the 40 and the 10, just like we did before. We can do the radicals separately if they're perfect squares or if I can simplify them easily. Neither one of them are perfect squares. I want to at least think about it if I do 40 divided by 10 first and then take the square root. So when I think about that, that might be easier. And again, 40 divided by 10, that's 4. And that's something I can do really easily. So I think this is a matter of just talking about what makes the most sense to deal with. So 40 divided by 10 is 4. So square root of 4 is going to be 2. So it's going to be I times 2. Now remember, I don't usually write it with the whole number behind. I kind of like to do the whole number first. So I would probably write that as 2I. So just trying to be a little bit more cautious about what's happening there. So trying to make it a little bit easier to write. So again, when you're dividing, we have some options, different ways to think of it. Okie doke, let's take a look at the last one. I want to see if you can tell, which one is it more like? Is it more like letter A or letter B? See if you can think about why it would be more like letter A or letter B. Well, hopefully you're looking at it's more like letter A because both of them have negatives underneath. So we're going to actually think of this as -1 times 48, square root of -1 times square root of 48, and a square root of -1 times a square root of 2. Get those negatives out right away. So in each of these, we have I times the square root of 48 then, over I times the square root of 2. And just like in that first one, look at those common factors. I can divide each of those out. So that's going to leave me a factor of 1. Or I just get square root of 48 over the square root of 2. So the i's actually end up dividing out. Now, once again, we get back to the same conversation. What's easier? 48 and 2, they are not perfect squares. Neither one of them are. So what I'm going to try to do is divide first and then take the square root and see if that's any easier for me. So 48 divided by 2, That would be 24. Now I know that doesn't get me to a perfect square. 24 isn't a perfect square, but at least it's not a fraction anymore. So now I can take that and break it down into the biggest perfect square that divides into 24 times what's left over. So look, use your perfect squares list. 4 divides into 24 6 times. That's the biggest perfect square that divides in there evenly. And square root of 4 is 2. So that would be 2 times the square root of 6. No imaginary part left because those i's divided out. But at least by dividing first and then taking the square root, I was able to deal with a little bit easier number. So the whole idea for this first part of section 8.7 is being able to deal with imaginary numbers, understanding what the square root of -1 means, that I, and being able to simplify when we have a radical that has a negative underneath that. So in part 2, we'll start looking at doing other operations like adding and subtracting.